Hi, everyone. Thanks for the announcements, Mary, and thanks for very nice to see you all again. Today we're going to delve further, zoom in even to smaller scales. Last week, to remind you, we were at atomic scales. We talked about photons and about electrons and protons and hydrogen. I talked a bit about quantum mechanics and introduced some wave-particle duality, and we saw the wave function of hydrogen and the sort of structure of discrete energy levels in hydrogen come out from quantum mechanics. And in fact, I wanted to start here. Again, there was a great question at the end of the talk last week, asking for more of an intuitive sense of why this, where did this discreteness of the energy levels of hydrogen come from? I sort of asserted it at the end of last week, but indeed, I think this is something I can give you some more intuition about, and so I want to start, by trying to give you an intuitive sense for why we end up with this sort of discrete structure of matter coming from quantum mechanics. And the answer really has to do with waves, with the fact that, as we talked about last week, in quantum mechanics, fundamentally, all matter is described as a wave with this Schrödinger equation. Now, right, to give you some intuition here, I want to talk about waves in a more familiar setting, sound waves like we did last week. You can imagine if I have just some very long string, then I can excite. I should have tried to bring some sort of string, but I can wiggle it and move it with all sorts of waves that I like. I can make some very sharp waves. I could make some long wavelength waves. I could just create some sort of wave packet. It seems like with some long sort of string, I can just make whatever sort of wave I like. And indeed, in vacuum, a photon, some light can have any sort of frequency that you like. The discreteness comes from, in a sense, from boundary conditions, which is a technical term, but I think one that you can get an easy sense for. If rather than having some very long string, I imagine clamping my string, taking a relatively short length of string, and clamping it down on both ends, like you might find in a guitar or a violin, whatever your favorite string instrument is, then now, with the string attached at the boundaries, which mathematically we describe with boundary conditions, now there is a preferred discrete set of modes. These are waves where the wavelength matches some integer multiple of the total length of this string. So one, the fundamental mode just has, well, really this is half a wavelength, or there are other sort of preferred modes where an integer number, potentially a large integer number, but where the wavelength of the wave that you're exciting matches the length of the string. And so these, having some boundaries here, has given a notion of some preferred wavelength, some preferred energies, and this really is what's happening in hydrogen, to have some discrete energy levels there. I have an animation, some great animations from Wikipedia. Okay, good. So
I have a quick question.
yeah, yes,
Yeah, boundary conditions are the 2 points.
yes.
What about the atmosphere in which the string is? Is that a boundary condition?
In this approximation, no. What you should think about here, this model we're exploring is just sort of a one-dimensional model of a string. I just have what's happening at the two ends as boundaries.
But is it in a vacuum or is it in
Sure,
gas?
you can imagine in vacuum. The effects of the air molecules will be quite small. You can understand a guitar string just like this, and in fact here. So this very nice picture from Wikipedia translating from where you would put your finger, which fret you would put your finger on to play different sorts of waves. But so the point is that you have these preferred sorts of waves. This is giving a comparison between string instruments and instruments like a flute or something, where you have an open pipe, roughly. They're different sorts of waves, but still it is this discreteness, the fact that you have a finite size object that is responsible for having a discrete set of energy. This is why you may think of sound in terms of a musical scale, some discrete set of frequencies that sound nice to our ear when played together, even though, of course, sound also could be some continuous thing. Yes?
These are exciting the medium. Waves that you excite the wire, the string with it, or you excite air molecules, like in the case of a flute.
Yes.
But this is not the sound that you hear. It's not the sound that is transmitted. The sound that is transmitted is a pressure wave in the air.
Indeed. So this is describing the formation of the wave in the instrument, but you're right that this ends up propagating through the air to our ears.
This kinetic energy of this vibration, if it is air molecule or the string, has to be converted to pressure in the air. So
Very
it
right.
moves like a wave.
Very
So
right.
in this case, this wave has nothing to do with the sound wave
Well, I'd
that
say
transmit in the air.
I'd say that this produces the sound wave, but indeed, all I wanted to get across with this was some intuitive sense for why discrete energy levels, discrete frequencies are appearing in the hydrogen atom. I haven't quite gotten to the hydrogen atom yet. This is what, if you just think of some sort of musical instrument, in the case of quantum mechanics, often the first sort of toy model of quantum mechanics that that students study in an introductory quantum mechanics class is what's known as the infinite square well, or a particle in a box. You just imagine that your potential, this function that goes into the Schrödinger equation, completely traps your particle in some finite region of space. And indeed, the wave functions that you find when you solve the Schrödinger equation are exactly analogous to the waves in air or the waves in a string. One finds when one solves the Schrödinger equation for a particle confined to a box, one finds, again, this special structure, this discrete spectrum of energy levels corresponding to these special standing waves, where the wavelength matches some integer multiple of the size of the box. Now, that isn't quite hydrogen. To get to hydrogen, we don't have quite this extremely confining potential, but what you should imagine is that in a hydrogen atom, you have, at least in this quantum mechanical model for a hydrogen atom, you have separately the electron and the proton, and they're not exactly confined to some finite region of space, but there is this electromagnetic force that is classically sort of binding them together. And this is, I showed last week, the potential energy for a hydrogen atom. It doesn't look exactly like the particle in a box, but still the electromagnetic force resists you pulling apart these negatively and positively charged states. So there still is a potential that has indeed some bound states, and it's a little bit more complicated than just an infinite square well, but indeed this same feature of having some finite number of wavelengths fit in your some relatively small region, this still is what's really responsible for the discreteness of the hydrogen atom. Good. So this is something I want to revisit from last lecture, because indeed one of the most surprising things about quantum mechanics is this discreteness of the hydrogen atom. Of course, this is responsible for having these discrete sets of energy levels is what's responsible for the photoelectric effect, like we talked about, or any sort of absorption phenomena. So I wanted to get across that there's at least some sort of classical intuition you can have about why the wave equation has led to this discreteness. Yes?
I think one should mention the periodicity condition is the boundary condition. Reinforcing a wave going around, and that is a three-dimensional generalization of that. The Broglie.
Yes, very true. So this first, just this box that I wrote down was just one-dimensional. Really, the hydrogen atom is three-dimensional, and indeed, there's something about the wave function having to return to itself as you go around radially or angularly. Indeed, is another important aspect when you solve the hydrogen atom in the full three-dimensional quantum mechanics. Yes, good. Okay, great. All right, now a concept that is going to be behind a bunch of the things I'm going to say today is that of special relativity. And I wanted to say this especially because there was a question the first day about the pronunciation of the building we're in, the Michelson Michelson Center for Physics. And indeed, Michelson became, well, one of the things he is very well known for is in the 1800s, people were very confused about, well, as we've been talking about, what exactly light is. And as did they, or we've been talking about it in analogy with sound waves. But sound waves, of course, always travel through a medium. Maybe that was what some of the questions earlier were also getting at. The sound, we have these pressure waves that travel through air or water or some solid. And physicists in the 1800s thought that light being a wave meant that light should have some sort of medium that it was traveling through. They gave this the name the luminiferous ether, one of the more fun historical physics names. But in fact, Michelson, along with Morley, did this great interferometer experiment. What they were doing is carefully sending light out in different directions and reflecting it back to the source to try to test whether the Earth was moving with respect to this hypothetical luminiferous ether that filled all of space and was the medium that light traveled through, by comparing the beams of light that went out in different directions to each other, they could do interferometry and establish, in fact, that no, there was no luminiferous ether. These light waves don't need some medium to travel through, but are just waves in vacuum. And this was one of the experiments that led Einstein and others in the early 1900s to come up with special relativity, to try to understand really what the speed of light is. So Einstein postulated.
Question here.
Quick question, yes.
You know, Michelson and Morley assumed that the ether is rigid and it fills the whole universe.
Okay.
So any light source emitted, in this case, the reference point would be fixed in that ether. Okay? So if Earth is moving and the light that is emitted moving from that point, in this case, Earth and light will be moving at different velocity, and if they measure the light while they are on Earth, in this case, they'll find difference between the speed of light.
Yeah, maybe we can talk about this at the end.
But just a minute, because because this assumption.
Come on.
We came to hear the story. We want to hear the lecture.
No, I appreciate the enthusiasm. We can try to talk later. We can talk about more of the details here. Certainly, although I'm presenting a semi-historical account, now we have much better understanding of the structure of space-time. You don't need to rely on the 1800s experiments to understand the structure of space-time today. But let me say, okay, so this experiment was important for Einstein and others developing this hypothesis to imagine that the laws of physics really are the same for every observer moving at some constant relative velocity, and in particular that the speed of light is constant, no matter no matter who is observing it. This goes against our sort of everyday intuition about how velocities add, the laws of sort of Galilean relativity from the some hundreds of years ago, but indeed there is this maximum speed, this speed limit, of the speed of light in our universe. If we were doing all 8 weeks on particle physics, I'd go more in depth into this. But for what we're going to use this for, what you can think, for one, what you should have in your mind is that this puts space and time on an even sort of footing. For physicists some hundreds of years ago, and in our everyday lives, space and time seem like very different objects, very different sorts of coordinates. In fact, special relativity puts them on the same footing, and you can think about phenomena happening very quickly compared to the speed of light, as requiring these laws of special relativity to describe accurately. And this includes Einstein's famous, sometimes people say mass-energy equivalence. What you should really just think was Einstein recognizing that energy contains a kinetic component, like we talked about last week. P here is momentum. And also there is this rest mass energy in every particle. Einstein's the way you normally see it is for a particle at rest. So with zero momentum, then you just have this rest energy, which is E equals mc squared. This is the more complete expression. I've written this is the right way to include both the rest mass piece and the kinetic energy piece, and it's going to be important for what we're going to do today. Oops, going the wrong way. Okay, so I want to talk a bit more about light. So already back in the 1800s, Maxwell had understood that light was a wave of the electromagnetic field. Maxwell understood, figured out experimentally these equations relating the electric and magnetic fields to charged sources and currents and how they relate with time. Maxwell noticed that if you were in a situation where you didn't have any charged sources or currents around, and you just looked at a vacuum solution to Maxwell's equations, just how the electric and magnetic fields themselves interact, then you in fact end up with these classical wave equations describing the electromagnetic field. Maxwell recognized that just from his experimental equations describing how charges interact, you could find that there were waves of the electromagnetic field which traveled at the speed of light at c, and this is why light is very important in this study of special relativity. Now, I've already introduced some quantum mechanics. We know that we should really understand light as a particle, as the photon, which you should think of as the quantum, the bit of this wave. You should think of as a quantized wave of the electromagnetic field. It's massless. It does not have any sort of rest mass energy like appeared in Einstein's mass energy equivalence. And the light being massless means that it travels at this fastest speed that anything can go, at the speed of light. Now, light also has spin 1. Now, if this were a quantum mechanics course I was teaching, we'd probably spend about at least a whole class talking about what it means to have spin 1. But what you should just keep in mind, okay, this won't be incredibly necessary, but what you can have in mind is that spin is some intrinsic angular momentum. And again, this is a fact that physicists were forced to accept. It's not something that necessarily should seem obvious to you, but in fact, particles themselves can have some intrinsic amount of angular momentum, and the fact that the photon has spin 1, this means that the waves of the electromagnetic field, and okay, good, the waves of the electromagnetic field, they're transverse waves. So what is being plotted here is the electric and magnetic field. It's transverse in that you should think the photon in this picture is the light wave is traveling in the direction of this arrow. The electric and magnetic fields are transverse. They're going out orthogonally, not in the same direction of motion as a sound wave would, but transverse. And spin 1 means that you can have different sorts of polarization. The light waves going, the oscillating electric and magnetic fields going orthogonally to the direction of motion can appear in two different sorts of oscillatory patterns. One way to think of it is either linearly, just going back and forth along some plane, versus circularly, oscillating sort of around the direction of motion. This is a different, this is another property of light. Unfortunately, our visual systems have not evolved to be able to distinguish between different polarizations of light, but that's not true, in fact, for many, many animals. Let's see if, so I pulled here from some biology paper, many animals, I think the mantis shrimp is often seen as a good example here, but also an example of a butterfly. Many animals can distinguish between these different sorts of polarizations of light, this other property that light has, and indeed, so this is how we would see some animals versus how they appear to some predators or prey, some different animals that can see this other property of light, which we haven't evolved to be able to see. Okay, but indeed, polarization is a fact. This is the sort of wave that light is. And related to the fact that it's spin 1, it's also a boson. You've maybe heard the word before. We'll see it again over the next couple lectures. So because the photon has spin 1, a full number, this means that photons, in a sense, like to be in the same state. This goes back to another question we had last week. Photons are a sort of particle where there is an increased chance to find two of them in the same exact state. That's what boson means, roughly, and this is really what's responsible for the phenomenon of lasers. This is how we end up producing some. Do I have a laser here to this laser? This is lasers. Good, perfect. Indeed. So the way that we're able to produce light, all collimated and in a sharp point, like in this laser pointer, is using this property that light is a boson. And if we set up the right scenario, then photons like to be all in the same state and can form things like lasers. Okay, let me get going, and good. Now, we also had some questions about charge, and this isn't going to be the last thing I'll say on the matter, but charge you should think of as telling you about how matter interacts with photons. This is another conserved property, just like we said that energy is some property of physical systems that is conserved over time. Charge is also some property that is conserved over time, and it tells you how particles interact with the photon, with the electromagnetic field. Now what I've drawn here is what's known as a Feynman diagram. I have these green lines being some electrons, and this black wavy line, a photon, which we denote with the symbol gamma for historical reasons. You can think of this roughly as a space-time diagram. Good, and what this is describing is that if you shoot two electrons at each other, because they both have negative charges, like charges repel, these two electrons can exchange a photon and scatter. This is the quantum description of how the electrons are able to interact. They do so by exchanging a photon, exchanging one of these quanta of the electromagnetic field. And indeed, I want to stay on this a bit. We described last week and a bit today, we described solving the hydrogen atom in quantum mechanics. But the way we did it was I used the classical description for the electromagnetic potential between an electron and a proton, and using that, we solved for the stationary states, the wave functions of the electrons around this proton. But that's not entirely satisfying. From Maxwell, we already know that the photon is the quantum of this electromagnetic field. We shouldn't have to talk about different sorts of ingredients. So the problem was when we did this in quantum mechanics, we had the electron and the proton as some particles, and we were solving for them in the background of some electromagnetic field. But that's quite unsatisfying. What is the relation between these particles and waves that we talked about last week and this field of electromagnetism? In fact, as we've already said, the photon is the quantum of excitations of this field. The electromagnetic field can have some background value, like we were using to solve the hydrogen atom, and against some background value, maybe, what do I want to say? Either in empty space you can have some photon, or in the background of some electromagnetic field, you can still think about some photon as some small excitation, some small quantum mechanical amount of energy. But really, we should be able to talk about everything in some unified description. And indeed, you can think about the bound state of the electron and the proton as rather than just putting in by fiat that there's this separate sort of classical electromagnetic potential, you can indeed think about the electromagnetic potential as being built up by exchanges of not just one, but an infinite series of photons that build up the electromagnetic field between the electron and the proton, right? And now we can talk about everything in the language of particles, quantum mechanical exchanges of particles of the electromagnetic field, rather than just some classical background. And indeed, what I'm really introducing here is the beginnings of quantum field theory. This is recognizing the photon as the quantum of the quantum electrodynamic field, and trying to put everything on the same footing. Maybe this is a good place for me to stop for questions. Briefly, yes?
Gordon, maybe I can't read your writing properly. Is it V sub R?
Sorry, this is a function. Indeed, the potential energy as a function of the radius.
Okay.
Yeah, this is just telling you what the potential energy is between the electron and the proton depending on how far away they are.
And then is it E squared over R also?
Yeah, E squared, E is the quantum of,
Thank you,
yeah.
I just wanted to make sure
Sure.
that I was seeing it
No, good.
correctly.
good question,
Thank you
yes,
very much.
yes.
Red on black is bad.
Okay, good.
Yeah, use some other color. because
yeah,
yellow-
I'll,
Yellow.
good, you're right, the next time I'll bring down different colors from my office, yes, good question.
And back,
Yes, yeah.
back at the Maxwell's equations,
Uh-huh.
so the B is magnetic field, the E is electric field.
Yes,
There were two other things there.
good,
The rho and the J, could you please?
absolutely, yes, thank you. Good, you're right, there are a lot of things to get through, but, a lot of these things I take for granted. Good, so rho here is a charge, an electric charge, and so this equation is telling you about what the electric field is of a charge. You have this radial Coulomb field from a charge, and J here is a current. It's telling you about how an electric current in a wire or something sources a magnetic field. Yeah, so both rho and J you can think of as sources for the electric and magnetic field respectively. We found the wave equation for the electromagnetic field for light coming out when you look at solutions which don't have any sources, then you see this sort of wave behavior of light. Good question.
I have one more.
Okay, yes.
Okay, on the board out here, they describe some U of C experiments. And they talk about E plus and E minus collider.
Yes.
Does that mean electron?
That means electron and positron. And in fact, that's a very well-timed question because that's exactly my next slide. Okay, so when you go to quantum field theory, when you're trying to understand matter at this deeper level, you find that not only is the photon an excitation of a quantum field, but in fact, all particles are excitations of some field. And this necessitates the introduction of antiparticles for every charged particle. And indeed, so the question, if you see some poster talking about an E plus, E minus machine, that's talking about colliding electrons and positrons. Now, why? Okay, I was trying to think about what a good way to introduce this is. I think perhaps a good thing to think about is, well, I drew this diagram on the board. So I had this diagram describing the scattering of two electrons by exchanging a photon over time. And I mentioned that special relativity you can think of as really uniting space and time together. It tells you how the laws of physics look if you're traveling very quickly, and when you are moving very quickly relative to something else, the way in which you measure space and time gets somewhat modified relative to some stationary observer, but all in some consistent way, and special relativity tells us how to transform space and time into each other, roughly. Antiparticles, good. So quantum field theory, you can think of in some sense as coming from the marriage of quantum mechanics with this need to be special relativistic invariant. And I think a good way to think of it might be as just a symmetry of this diagram. Here I had space on the horizontal and time moving up vertically. But I could have, if space and time are really the same sort of thing, I could have imagined switching these axes, or in a different way, just permuting the diagram. Here, so this way, still time, space. So I could just think about if space and time are really the same sort of thing, why don't I just draw this other diagram which has roughly the roles of them reversed? What does that mean? How should I interpret that in my quantum mechanical theory? And indeed, the way to interpret this is that at these vertices, rather than having an electron emit a photon, what can happen at these vertices where two particle lines come together in this sort of arrangement is that you have an electron and you have its antiparticle, a positron. A positron, antiparticle of an electron, it has exactly the same mass, but exactly the opposite charge. Now, this is necessary if we're going to ever imagine creating and annihilating particles. And indeed, this is another way you can think about the need for quantum field theory past quantum mechanics. Quantum mechanics didn't really tell us about how particles interact. We had to put in by hand, and as I emphasized, it was somewhat unsatisfying that we had the electron and the proton interacting through the photon. Good. Now, with quantum field theory, we can understand how particles are created and destroyed.
Wow.
And one way, indeed, I agree. It is, classically, you might have thought that the sorts of particles that we have were all fixed. That maybe you could understand their dynamics, but the number of photons or electrons or what have you was fixed. Quantum mechanically, that's not in fact the case, and we can have an electron and a positron come together and annihilate each other into photons. And in fact, the reverse process, you can have a photon have enough energy to create an electron and positron out of the vacuum. And this really only makes sense in the context of quantum field theory. What do I want to say? Good. Well, something you could have just asked in general is why do we have, it seems, the story I've been telling you is that we have some simplicity. We have only a few different types of particles. And indeed, if you go and look in the world, you'll find that all electrons behave exactly the same. Why is that? In fact, it's because all of our particles are some excitations of some quantum fields. So each electron, the electrons in your body and my body, indeed are exactly the same because they are all excitations of some electron field that is one of the quantum fields that pervades the universe. Good. And this is also the sense in which you can have some annihilation or creation processes. You might ask, where are these electron and positron coming from? Well, what's happening really is that you had some electron, just like you have some electromagnetic field in which the photon is an excitation, you have some electron field pervading the universe, and when you have a high enough energy photon, you can excite some real particles, some electrons and positrons, out of the vacuum as excitations of that field. Good. Okay. Now, delving, I want to make sure we get actually to the nucleus, and so, indeed, now we're really going down from the atomic scale to now something like 10 to the minus 15 meters. Around the same time, we were understanding light, and also an experimentalist, well, we were doing lots more scattering experiments. You know, what happens when you shoot X sort of particle at Y sort of particle. In particular here, the experimentalist Chadwick shot some helium particles at a beryllium source and produced some uncharged sort of thing that we now call the neutron. What should I say? Indeed, these numbers here are the total number of protons and neutrons in each particle. They're conserved in this nuclear process. And so last time we talked about these experiments showing that the positive charge in the atom, rather than being some sort of fluffy ball in which negative charges were embedded, the positive charge is all at the center. But what is it really? Apparently it contains neutrons. Good. And indeed, nuclei are made out of neutrons and protons. Some neutral components and some charged components. But this is quite puzzling. Because just like we saw that the electrons repel each other with the electromagnetic force, the protons in the nucleus should also be repelling each other from the electromagnetic force, right? You have lots of protons in the nucleus. You should think that these will likewise repel, and you wouldn't have any stable nuclei. So physicists in the 30s were puzzled about how these collections of positive and neutral components were staying together. And what they discovered, there must be some sort of new interaction, right? Because this repulsive interaction would blow everything apart. So the physicist Yukawa in the 30s proposed that there was a new sort of interaction. Oops, where do I have? Okay, fine. Proposed that there was a new sort of interaction. It couldn't be another photon-like thing because it needed to be attractive for the same sort of particle, for protons and for neutrons. And so what he proposed is that there is a new type of force that, rather than being mediated by a spin 1 boson like the photon, is mediated instead by a spin 0 particle, what's known as a scalar. And with the scalar, which we draw as a Feynman in a Feynman diagram as a sort of dashed line, with the scalar, then you always have an attractive force. How much of this do I want to write down? Good. I will try to briefly write something down. Minus n r. Okay. Good. So we propose a new sort of particle, a spin 0 scalar particle that protons and neutrons could be exchanging, which would give an attractive force and act against the repulsive electromagnetic interaction. But there is a puzzle, which is that if you send two protons at each other, yeah, good. So even though these collections of protons and neutrons in nuclei indeed are somehow held together stably, if I just shoot two protons at each other, they scatter in much the same way that electrons do. They are still repelled by the electromagnetic field. So this new Yukawa interaction has to be something that only holds things together if they can get very, very close together. If they're in the presence of a whole bunch of protons and neutrons. And so the other key difference from electromagnetism is that the photon, as we started today with, the photon is massless. And that means that it can propagate, well, at the speed of light and also any sort of distance. It can be a long-range force. But for Yukawa to understand the structure of the nuclei, he had to posit that there is a non-zero mass of this particle. I should have looked up what the value was prior to coming down. It's something like this, although those symbols don't mean very much. But the fact that you could have protons and neutrons exchange a massive particle, I should put this up further, means that you can have this very attractive force that is only present on extremely tiny scales. Maybe I should write down, well, gosh, it's something like 10 to the minus 15 meters. Okay, I'll spare you trying to convert this. This is a decimal place and 14 zeros and then a 1. I won't write that down. But the point is that this attractive force only takes place on those very small distances once you get protons and neutrons very close to each other. And this is why these nuclear processes happened in the very early universe, and as we'll talk about later, they happen in stars at very high temperatures, but our everyday lives are controlled just by these electromagnetic interactions of the electrons and the protons. These nuclear interactions with the pions really only happen at very short distances. Now, there was another mystery in understanding nuclear physics, which is that many of these isotopes, depending on how many protons and neutrons there are, many of them are unstable. And they decay with a very broad range of lifetimes. But physicists had observed that at least some class of decays seem to be coming from a neutron decaying into a proton plus an electron that would be shot out of the nucleus. This is all that you would experimentally see. But this was also puzzling. We know from Einstein that there is some energy associated with mass, with the rest mass of matter. But now, if all that was happening in these interactions really was that a neutron was being converted into a proton and an electron, then from energy conservation, what you should see is that the kinetic energy of the electron, which is just the energy of motion, should be simply related to the amount of mass that is being converted from rest energy into kinetic energy. You had some mass of the neutron some amount of it goes into the mass energy of the proton or the electron, and you think the rest of it should be in the motion of the electron. And apologies, I'm doing the particle physicist convention of setting C to 1, which is convenient for us but annoying to everyone else. So there should really be some speed of light there. Okay, but surprisingly, this was not what people saw. This is some data from a paper in 1940 looking at the energies of the electrons produced from these nuclear decays. And rather than seeing a monochromatic, some given speed from this equation, there was a distribution of speeds observed for the electrons that were emitted. And this was puzzling for a long while, until in the early 30s, Pauli and Fermi suggested that there was another particle being produced, the neutrino. And I should emphasize again, this is, well, here we are at the Enrico Fermi Institute. This is, of course, that Fermi, and we have some, as you exit the building, you can look at some nice historical displays about Fermi's life. But Pauli and Fermi suggested that, in fact, what was happening was that the neutron was decaying to a proton, an electron, and some other very weakly interacting particle known as the neutrino, that we just had not, we just were not seeing because it is electrically neutral. And indeed, they felt that this was still the beginning of particle physics in many senses. They felt bad about introducing, for reasons of fitting the experiment, some particle that was very difficult to detect. In fact, very weakly interacting, some hundreds of billions of them produced from the sun in the sun's nuclear reactions, some hundreds of billions of them pass through your body every second. And in fact, a given neutrino can go through the entire Earth without interacting with something. But indeed, this is correct. Ultimately, we built really fantastic, very large sorts of detectors to be able to finally detect these neutrinos. I haven't been explaining all the images on my slides. This is some picture from a detector in 1970, which detected a neutrino that comes in, doesn't have an electric charge, so isn't interacting with anything until just by chance it happens to collide with a proton in this detector and produce some outgoing particles. So this is the neutrino. Good. What I want to say very briefly, and what we'll talk about more next time, once you understand we have quantum field theory, and electrons and positrons can annihilate to create photons, and these photons can also produce electrons and positrons, well, the photon can just as likely produce any sort of charged particle that exists. All of these, in empty space, you have these fields corresponding to whatever sort of charged particles are out there, and you can try to produce some very high energy photons that pop out from the vacuum, some positron, some particle-antiparticle pair of some new particles. So indeed, physicists went and used electron-positron colliders to try to understand what other sorts of particles, electrically charged particles, exists. And you can find, so this is a nice compilation of experimental data where indeed at many different, they find a whole sort of zoo of different particles which are some exotic versions of the proton and the neutron, some exotic versions of these nuclear particles that we know about from our own matter. And I think I think I'll talk about that more next week. Let me just end with saying, so nuclear physicists understand fantastically well the interplay of all of these different effects. I mean, it is some very rich interplay. We have electromagnetic interactions of charged particles. We have the Yukawa forces that are binding together neutrons and protons. We have these decays of neutrons into protons and electrons and neutrinos. So there is a variety of forces of effects at play, but you can understand, nuclear physicists have understood, depending on how many protons and how many neutrons you try to put together, what the lifetime is of these various nuclei, and the decay of these nuclei takes a very simple exponential form, and in fact, we can use this. This is as I say, radioisotope dating by understanding the abundances and lifetimes of various isotopes in samples on Earth of, some petrified tree or some Neanderthal fossils or some rocks from the initial formation of the Earth. You can understand the age of some sample that you find based on which sort of nuclear isotopes exist in that sample. And this is how, not only are we able to date, some bones, what have you, but also how we're able to determine that the Earth itself is very, very old, some 4.5 billion years old. So just want to get across, some of this is very abstract, I know, but indeed, these are things that are really, the structure of matter at its smallest scales and understanding it really does help us understand all sorts of branches of science. Great, so next time, we're going to continue zooming down even further. I'll talk about hadrons and understanding excited states of nuclear matter. And then I'll talk a bit about the Large Hadron Collider, now this enormous proton collider that we're using to uncover what matter looks like at its smallest scales, and we'll build up the whole standard model of particle physics. These past couple lectures, there's been a lot of confusion and trying to understand what the data is telling us. Now we have this beautiful picture of the standard model, and I know there's a lot of excitement for it, so I'll try to talk a bit about the Higgs boson and spontaneous signature breaking. So thanks for listening, and I'll see you then. Go to the back, yes?
How do they know a neutrino can go through the Earth? What experiments did they do?
Oh, good. Lots. I mean, originally this was a prediction that was made experimentally. But in fact, I think probably the best answer to your question is there's this fantastic detector located in Antarctica. What physicists have done, astrophysicists and experimentalists, is they've used the fact that in Antarctica there's all this very pure ice, and they've put some instruments to build sort of a very macroscopic detector using this very clear ice that's in Antarctica, and what they can do, so the clearest evidence for the fact that neutrinos can go through the Earth is that this ice cube experiment, I should write that down in case you want to look this up, the ice cube experiment can see, they're located in Antarctica, so they can see things, of course, that are coming from the sky above Antarctica, But in fact, well, this shouldn't be strange. In fact, they have seen many neutrinos that indeed have gone through the entire Earth. They see some neutrinos not just coming down from the sky above, but also neutrinos coming from under the ground, having passed through the entire Earth before interacting with something in the detector. So indeed, it's amazing, and certainly there's many good stories about the heroic experiments that were done to detect these. It's rather amazing that it could be predicted that you have this incredibly weakly interacting particle, and then we could actually go see it. I agree. Yes?
What would happen if the interaction probability was a lot larger in neutrinos with normal matter?
What would happen?
Everything just seemed to start melting away, and
Well, to some extent, if you turn it up high enough, then you'd be endangering life. Neutrinos are one source of background radiation that exists in the cosmos. As I said, hundreds of billions of them are passing through our bodies every second. And indeed, some relatively, what should I say? Some part of why humans and every other living organism is susceptible to things like cancer is because you can have very high energy particles, things like cosmic rays, come from space and disrupt what is otherwise a very efficient mechanism that your cells have of reproducing DNA. And cause mutations that can be harmful. If neutrinos interacted with us much more, then I can imagine that being that source of neutrino radiation being quite a large problem for life. So that would be one bad outcome. Yes.
Yeah, about positron and electron. When they collide with each other,
Yes.
they annihilate each other. And does that mean the mass annihilated and the charge annihilated?
Yes.
So the mass is kind of different in each one of them?
No, so they have the same mass, and so this goes back to sort of the special relativity, the mass energy equivalence. So if you have some electron and positron come together and annihilate into photons, then you know that the energy of the photon is going to be the sum of the energies of the electron and the positron. And at the very least, that consists of the rest mass energy of the electron and the positron. So the electron and positron might also have some kinetic energy, but the annihilation turns the mass energy of the electron and positron into some kinetic energy for the photon.
So the mass of the two, the positron and electron, okay, converted to the energy of the photon.
That's right.
Okay, and that is, they calculated the same. I mean, does this photon has that much energy?
Indeed.
Equal if you use E equal mc square?
That's right. Yes.
This is the energy of the photon equal this transformation of the mass.
Yes. Yeah. Precisely. So what we talked about yesterday, last time, and today, indeed, there is this quantity called energy, which is conserved, but you can have different sorts of energy. Energy is a property of physical systems. It can be stored in kinetic energy, energy of motion, or the energy of a spring, or chemical energy, or mass energy. Indeed, when you have some process like annihilation of particles into photons, the mass energy that was originally in those particles goes into the kinetic energy of the photon. That's right. Well, why don't we come back to this?
No, but it's same thing.
Okay,
It's
okay.
same question. You
Okay,
should allow a little bit in exchange of
sure,
things, okay?
sure.
And
See you
so
after.
the photon afterward, it can also create a positron and electron
Yes, yeah, you can have
with
the reverse.
negative and positive charge.
Yes.
So does that photon carry in it a charge
No.
when it travels?
Good.
Where does this charge come from?
Oh, good. Well, good. So as we talked about, also charge is always conserved, but that includes that you can go from having 0 charge to having 1 negative charge and 1 positive charge.
So charge can be created.
No. Well, charged particles can be created, but total charge is conserved, just like the total energy is conserved. You can, when you have a negative charge and also a positive charge, you can annihilate them into something with 0 charge.
But you can create them again.
Yes, yeah, but your process doesn't change
nothing.
the amount of charge
From
in
nothing.
total.
From nothing.
From you can transfer energy from the electromagnetic field, which is not charged, into positrons and electrons, which are charged. That's right. So indeed, you are creating charged particles, but the total charge always stays the same.
Yeah, but still, you are creating a charge
Yes, you're
Can you say
creating
that?
charged particles.
from nothing.
From you're taking energy from one sort of quantum field and transferring it into a different sort of quantum field. But we can talk about the details a bit more. Yes, there was a question back there?
I have a question.
I read somewhere that at one time astronomers used to think, and I know this is an astronomy question actually, used to think that there were actually galaxies, or I should say stars, that could possibly be composed of antimatter.
Yes.
And that if you look at a star that was shining, that was composed entirely of antimatter, it would look the same as a star that was made of ordinary matter.
Indeed. So this is a great question. So something I haven't addressed, but we can talk about in the second part, which is more cosmological focused. But indeed, something I haven't addressed is why in our everyday lives we see electrons, we see particles, and we don't really see antiparticles. Now the modern theory for why this happens, some event in the early universe going by the name baryogenesis. But indeed, your first thought was that maybe around us everything is particles, but somewhere else everything is antiparticles. And this was indeed something that was searched for. The problem is that, and the reason that we don't think the world works this way, is that there would be some regions where a region of matter and a region of antimatter sort of meet. And you'd see lots of very energetic particles coming out from that. And we don't see any such regions. To very good approximation, we know that really all of the galaxies and everything we're seeing are composed of matter. And we think we need to look back into further cosmology to understand where that difference originally arose. How about this last question, and then,
On your last slide, would you get?
Yes.
Yes.
This one.
Would you interpret the two lines, experimental and the Z-equal?
Oh, good.
Please.
Good. So this isn't, I'm not a nuclear physicist, so this isn't something I can talk about in detail. But indeed, this axis here is the number of protons in your nucleus. The vertical one is the number of neutrons. And you see, maybe your first guess for what might have been most stable is when you have the same number of neutrons and protons as each other. It turns out the line of stability veers away toward having more protons. These darker shades here are more neutrons. The darker shades here are the most stable isotopes. Yeah, maybe I can try to say a bit more about that next time.
Thank you.
Thanks, everyone.
Decay.
You even sound like it.